Welcome. Today we will discuss powertronic control of induction motor drive. First of all, introduction. So, all of you know previously in DC motor was the best choice for all the industrial drives, only choice for the industrial drives, because induction motor speed control is not so easy. It was not easy that time, but DC motor has the main drawback, that is it has presence of commutator and brushes which require frequent maintenance, and this that make them unsuitable for dusty environments and explosive environments where fire risk is there. So, DC motor is also costly. So, for that DC motor has certain disadvantages. From those point of view, induction motors, particularly squirrel cage type induction motor, are rugged, cheaper, lighter, smaller, more efficient, require less maintenance or no maintenance, and can operate in all types of environments. So, availability of thyristors, power transistors and IGBTs have allowed the development of variable speed induction motor drive, and it has made the speed control of induction motor easy and with a wide range of speed control, which was not there in conventional method. So, for that reason almost all the industrial drives, fans, blowers, cranes, conveyors, traction, underground and underwater installations use variable speed induction motor drives these days. So, the principle of speed control of induction motor is well known. It is covered in the machine classes, and the electronic method of powertronic method of speed control, static control methods are like this: stator voltage control, which is done through AC regulator, then control of proto resistance through external rheostat and chopper, then slip power control through converters and inverters, diode rectifiers, then variable frequency control from voltage sources like VSI or cycloconverter, and variable frequency control from current sources, current source inverter. So, these are the schemes of static speed control of induction motor, which we will discuss one after the other. Today, we will discuss the first one, that is the stator voltage control using AC voltage regulator or simply AC chopper. So, the principle of induction motor speed control using AC chopper or AC regulator or simply voltage controller is based on this. The developed torque expression is given by, say, T E equals to 3 by omega S, rotor current referred to stator I 2 dash its square into rotor resistance R 2 dash by S is the slip. At slip S, the torque expression is given by this, and I 2 dash, so is the rotor current referred to stator, and if the magnetizing current is neglected, I 2 dash is stator applied voltage V 1 divided by R 1 plus R 2 dash by S its square plus x 1 plus x 2 dash square whole root. Denominator is the impedance, total impedance, and applied voltage is V 1. So, I 2 dash is V 1 by total impedance. So, using I 2 dash in the torque expression, the torque expression is given by 3 by omega S V 1 square into R 2 dash by S whole divided by R 1 plus R 2 dash whole square plus x 1 plus x 2 dash whole square. So, this is the torque expression. So, from this torque expression we can see as the speed, as the motor slip changes, okay. So, as the motor voltage V 1 is changed, T E and S both change, because in this torque expression T E is a function of applied voltage V 1 and slip S. Okay. So, when V 1 is controlled, and because all the time electromagnetic torque T E equals to load torque plus viscous friction torque at steady state, inertia torque at steady state is 0. So, this is the torque, because electromagnetic torque is detected by the load torque, and when the voltage is varied, torque is fixed. So, slip changes and according to slip changes with voltage. So, the torque balance is obtained. So, motor speed changes with voltage. This is the principle of speed control. So, with constant torque load, range of speed control is very small, because I will explain in the next slide. I will go to the previous next slide. So, these are the torque speed versus torque characteristics at different voltages. So, first this is speed versus torque at rated voltage, that is V s equal to 1 per unit. When the voltage is reduced to 90% of the rated voltage, the speed torque graph is this one. When the voltage is reduced to 75% of the rated voltage, graph is given by this one, and at 60% of the rated voltage, graph is given by this one. Suppose this is the speed versus torque characteristics at different voltages. As voltage is changed, the maximum torque is proportional to square of the voltage. So, maximum torque reduces as the voltage squared. So, graph also changes, torque versus speed versus torque graph changes. So, suppose load torque is constant, given by this green line, load torque. Okay. So, and you can see this point is the intersection point, which this is the intersection point which is stable, and because steady state stability criterion is satisfied there, but this point is unstable, because steady state stability criterion is not satisfied at this point. You recall the steady state stability criterion, which is dTL by d omega should be greater than dTm by d omega. This is for steady state stability. So, this is a stable operating point and this is unstable operating point. So, with constant torque load given by this, the minimum speed is given by the slip corresponding speed corresponding to maximum torque, that is the minimum speed that can be obtained. So, range of speed control is very small, as you can see for different voltages. These are the operating points. So, it is the range of speed control is limited, but consider other type of load for which load torque is proportional to square of the speed. For example, fan, pump, compressor, propeller, they have all the type load torque is proportional to square of the speed. Okay. So, this is the graph related to load torque proportional to square of the speed. So, with this you can see this is one operating point at rated voltage, this is at 90%, this is the operating point, at 75% this is the operating point, at 60% this is operating point. And you can see all the points are stable, steady state stable. Even this point is also at 60% of the rated voltage, this is also a stable operating point, because the steady state stability criterion is satisfied here. You see the steady state stability criterion given by dTL by d omega greater than dTm by d omega is also even satisfied here for corresponding to 60% of the rated voltage. And not only 60%, you can see for any voltage up to 0 voltage, the near 0 voltage, the operating point is stable operating point, steady state stability criterion satisfied. So, for this type of load, second type of load for which load torque is proportional to square of the speed, example fan, pump, compressor, propellers, speed can be reduced from the maximum speed down up to 0 speed. Speed control is possible. So, range of speed control is wide with fan, pump type of loads, but for constant torque load the minimum speed is given by minimum speed is given by this line corresponding to maximum torque, at which maximum torque is obtained here. This is the minimum speed. But for fan pump type of loads, for which load torque is proportional to square of the speed, speed control up to 0 speed also possible, because the steady state stability criterion is all the time met. And normally students think in the torque speed characteristics, this part is stable part and they say this part is unstable part. That is only for constant torque load, not all type of load. The stability criterion is dTL by d omega greater than dTm by d omega. So, for fan pump type of loads, this is stable also. So, when starter voltage is reduced from rated value, the developed torque reduces as proportional to voltage squared. So, this method is suitable for applications where torque demand reduces with speed, example fan, pump, compressor, propeller, like that. Range of speed control is large from 0 to rated speed, and that is the advantage for both. That is why all the fan and pumps, they are controlled by voltage, speed control is done by voltage control method. In an AC regulator or AC chopper, the applied voltage V1 to the motor is reduced by changed by changing the triggering delay angle. That means, if the triggering angle alpha is increased, V1 reduces. At alpha equal to 0 degree, voltage is maximum, and alpha is increased, the output voltage reduces, RMS voltage reduces in AC regulator or AC chopper. This is the characteristics we have already discussed. So, domestic fan motors are mostly single phase induction motors. Almost all the domestic fan motors are single phase induction motors, and they are controlled by voltage regulators. Now, they are used with small electronic regulators, that is nothing but a triac. So, a triac consists of two equivalent to two ACRs in antiparallel. So, a triac is used for voltage control of the single phase induction motor used in fans. Speed control is varied by varying the delay angle of the triac. The solid state fan regulators are preferred over conventional resistance or reactance regulators because of higher efficiency. Conventional regulators are also that fan regulators use voltage control technique using resistance or reactance. So, that increases the loss. So, efficiency is poor. In this case, there is no loss. And high power drives, in example industrial fans and industrial pumps, use 3 phase induction motors and 3 phase voltage controllers to regulate or control the voltage of the applied to the fan or pump. So, this is the scheme of AC voltage regulator. So, one AC voltage, this is the AC voltage regulator. AC regulator or AC chopper, AC to AC chopper. So, in 3 phase AC regulator, there are 6 thyristors like this. This is T1, T3, T5, T4, T6, T2. That means, 2 thyristors are in reverse parallel connected in each phase. So, thyristors are triggered at 60 degree interval in the sequence T1, T2, T3, T5, T6, T1 at intervals of 60 degree. So, with that, the voltage applied to the motor changes, the RMS output voltage of the chopper applied to the motor changes with firing as the firing delay angle alpha changes, the voltage applied to the motor changes. We will see the detailed analysis in next class. Today we will discuss the basic schemes. So, this is a 3-phase AC voltage regulator, and the AC voltage regulator is connected in the line, 3-phase line. Another scheme is there, we will see. Say 3-phase, here 3 phases are A, B and C. This is circuit C1, and here 3 phases are A, B and C, and here this is T1, this is T3, this is T5, this is T4, this is T6 and this is T2. So, this is voltage controller circuit C2. So, and you can see here the thyristors for the voltage controller are connected in series with the winding, and they carry only in circuit C2 thyristors carry only phase current of the load, phase current of the motor, but in the circuit C1 thyristors carry line current of the load. So, phase current is 1 by root 3 times the line current. So, in circuit C2 thyristors carry 1 by root 3 times the line current. So, current rating, average current rating of the thyristors is less, and so cost is less also, because the current rating is less, cost is less. So, this is the advantage of circuit C2, but in there is a disadvantage also, all the 6 terminals of the 3 windings must be available, so that thyristor of the voltage controller are connected in series with the windings. So, all 6 terminals should be available, and any third harmonic currents are in phase. So, third harmonic current will circulate in the delta, it will not flow, third harmonic current will not flow in the line, but it will circulate in the delta. So, it will not flow in the line current. So, that is one disadvantage of this circuit. Then previous voltage controller circuit C1 or C2, they can with varying with alpha control, the output voltage is varied. So, speed is varied in forward motoring mode, in one direction speed is varied, but speed reversal is not possible there. So, here another circuit is there. So, like T1, T3, T5, and this is this, is this, is, 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 this this is for B, this is for C. The pairs for A, B, C, they control the voltage applied to the motor, and speed control is done in one direction. So, another pair is there, which is this is C dash, this is B dash. So, you see, with thyristors 1, 2, 3, 4, 5, 6, phase sequence is A, B, C. But when we change to from C to C dash and B to B dash, phase sequence becomes A, C dash, B dash. So, phase sequence is reversed. Phase sequence of A, C dash, B dash is opposite to the phase sequence of A, B, C. So, here by changing from T3 T5 to T3 dash T5 dash and T2 dash T6 dash to T2 T6 to T2 dash T6 dash, the phase sequence is reversed. So, motor speed reverses. So, this is a reversible voltage controller. So, with this phase sequence is done electronically using the reversible voltage controller. And how the speed torque graph is changed? So, this is the speed versus torque graph with phase sequence A, B, C. When phase sequence is changed to A, C dash, B dash, this is the graph speed versus torque characteristics for reverse phase sequence A, C, B dash. So, with that, with phase sequence A, B, C, forward motoring is obtained. And with phase sequence A, C dash, B dash, reverse motoring is obtained, and here plugging is obtained in second quadrant and in fourth quadrant, second and fourth quadrant. So, fourth quadrant operation is possible with reversible voltage controller. Four quadrant operation is obtained with reversible voltage controller. So, next we will discuss a closed loop speed control method. Reference speed and actual motor speed are compared in a comparator. The speed error goes through a controller, which is the speed controller, and in this figure I have shown a PI speed controller. Any type of controller can be used there, any type for a speed controller. So, speed controller output has to generate the reference stator current, and sometimes because of controller design, current can exceed, can take high value. So, a limiting is used. So, this is the current limiter. Current limiter is often used to limit the motor current to safe values within certain limit, and output of the current limiter is the reference current IS star, and actual motor current IS is compared with the reference current, and the current error goes through a current controller. Here I am showing a PI speed control, PI current controller, and output of the current controller is the control voltage, final control voltage Vc, and this Vc is converted to alpha for the firing circuit of the voltage controller. So, Vc to alpha is converted and alpha control is done for the 3-phase AC voltage controller. AC supply to the controller. This is the motor. This is a diode that allows current in one direction. So, this is the current sensor, and this is the diode to allow block current in the reverse direction, and current feedback is taken. And this is the tacho generator for speed feedback. And this is the closed loop speed control scheme. And as you can see, the speed loop is the outer loop and inner current control is used. Which is discussed previously. Inner current control scheme is used with outer speed loop. And the closed loop control action generates the control voltage Vc, which is converted to alpha for to give the necessary output voltage, and this alpha of the voltage control is controlled in closed loop manner. This is a closed loop scheme. So, next we will discuss more detail about fan and pump drive. So, for fan and pump load, the motor torque Te is given by 3 by omega s synchronous speed into I2 dash square into R2 dash by s, and load torque is given by TL, that is C omega m square, that is C 1 minus s square whole square into omega s square. Okay. Because this type of load torque is proportional to square of the speed. So, if friction windage and core losses are neglected, then T L equals to T, motor torque T. So, with that, with this condition, you can see I 2 dash is some constant k times 1 minus s into root over of s divided by r 2 dash. Where k is proportionality constant, c is given by this. So, I 2 dash is given by this. So, if no load current is neglected, stator current I 1 equals to I 2 dash. So, with this I 1 is k times 1 minus s into root over of s divided by root over of r 2 dash, because I 2 dash we have obtained like this. At s, when s is the rated slip, s rated, I 1 equals to the rated current I rated, rated stator current. So, you can write I rated equals to k 1 minus s rated into root over of s rated divided by r 2 dash root over, by substituting s equal to s rated and I 1 equal to I rated. So, with this I 1 by I rated is given by 1 minus s into root over of s divided by 1 minus s rated into root over of s rated. Achha. And from this torque current expression, you can see current is a function of slip s. So, the slip s equal to s m, at which current becomes maximum. Is given by the solution of d I 1 by d s equals to 0. Okay. So, because using, so d by d s of I 1 is k 1 minus s into root over of s divided by root over of r 2 dash. This bracketed term is the I 1, d by d s equal to 0. Solving this, you get slip S m is 1 by 3, and with this I max by I rated, maximum current, and I 1 equals to I maximum. So, I max by I rated is 2 divided by 3 into root 3 1 minus s rated into root over of s rated. Okay. So, So, this is the relation between current and slip for different conditions like maximum current and corresponding slip and rated current and slip. We will use this analysis further for determining the optimum value of the slip or the range of slip at which operation is best preferred. That we will discuss in next class. Thank you for attention.